lesson, we're going to look at the global navigation satellite systems. We're actually going to be looking at section 13.1 to 13.3 in the book. This is going to be an overview of the global positioning system and the GPS signal structures. Later on in other lessons, we'll look at the reference coordinate systems, the fundamentals of positioning, and errors in the observations. GPS was created to replace transit, which was a system that was created during the 60s and into the 70s. The transit system could produce absolute positions to within 1 meter. However, it took days to get this accuracy, and it often meant babysitting the receiver so that you could replace batteries as they drained. It used the Doppler shift signals to determine the range to the satellites. GPS was created by the Department of Defense with funding from Congress. It's known as the Navigation Satellite Timing and Ranging Global Positioning System. First set of these words, navigation is what it's used for, timing, and for ranging. This is why it was created. And so its acronym is Navstar GPS, although we've just simply used GPS today. As I said, it was funded by Congress for the Department of Defense. And when Congress allocated that money, it required that the Department of Defense give access to the civilians. The initial price tag for the Block 1 satellites was $12 million. We're now into the Block 3 satellites. It became fully operational in 1993. The receivers themselves were designed to be passive, which means that they only receive the signals from the GPS satellites and do not transmit signals. When you think about GPS, you should think about trilateration, where you sit on control stations with your EDM and you measure distances to some unknown station, which therefore you get your coordinates from. Well, GPS works very similar. In fact, in this case here, the satellites are the coordinate systems. Now, these satellites are moving at about 1 kilometer per second, so they're moving fairly fast. So their coordinates change with time. They transmit a timing signal used in the code-based positioning, as well as timing other signals that are used by the civilian sector. And it also transmits a navigation message. Now, that navigation message is important because these are our control stations. Well, we need to know where they're at. And we'll get into eventually how we compute those things, but right now we'll just look at it this way. This navigation message contains an ephemeris, which is the position of the transmitting satellite. So if it's PRN number 1, it's going to be transmitting its position. But it also transmits a rough position for all the satellites. That's known as the almanac. And that allows the receiver then to find and determine which satellites it's actually listening to. There's other information, for instance, the navigation message is being transmitted, as well as now the civilian navigation message, the CNAV as it's known, is being transmitted. The GPS system is arbitrarily broken into 3 segments. One is the space segment, which is the satellites. The other is the control segment, which is the 50th Space Wing of the U.S. Air Force from Schriever Air Force Base in Colorado. And then there's this user segment. And the user segment is broken into 2 different types of segments because of the different types of receivers we have. There's the civilian segment, which of course is the surveyors and everybody else that uses civilian signals. And then there is the military segment, which is only military and authorized users. Now, they have different receivers than we have because they receive signals that we can't use. Originally, GPS was supposed to have 24 operational satellites and 6 orbital planes. These planes were spaced 60 degrees around the equatorial axis and inclined at about 55 degrees with respect to the equator. Today, we have somewhere in the neighborhood of 30 to 31 satellites, depending on how many are operational at any one time. But the original design was 24 satellites. The mean orbital altitude of the satellites is 20,200 kilometers. And the reason I say it's the mean orbital altitude is because these satellites orbit in an ellipse. So they're elliptical orbits. So they get closer to the Earth and farther away from the Earth in different parts of the orbit. And these orbits occur once every 12 sidereal hours. Now, the satellites are identified typically by their pseudo-random noise number. However, there are other methods of identifying those satellites. We don't typically use these. And in fact, one of the manufacturers used the satellite vehicle number. Well, in fact, that's not what it's hearing. It's actually listening to the pseudo-random noise number. And I'll explain what that means by being a pseudo-random noise number, or PRN, later on in this lesson. It also has an orbital position that we could identify it by, or its flight number. Basically, the system was designed to provide 24-hour coverage between the latitudes of 80 degrees south and 80 degrees north, 24 hours a day. That means there's at least 4 satellites above 15 degrees at all times during the day. The satellites have 2 atomic clocks. They're either cesium or rubidium. Most of them are rubidium. They have transmitters which transmit the signals that we're listening to with our receivers. And then they have receivers that collect data from the master control station. They're the only ones that can talk to these GPS satellites. So every once in a while you hear on TV about how we're communicating with the GPS satellites. No. In fact, we only receive signals from them. It's a passive system. The only people that can talk to those satellites are the military, and the reason they can talk to it is so they can shift their orbits, upload broadcast ephemeris data, and things like that we need to actually use these satellites. They also have solar panels and batteries. So they have the batteries so that when they're on the dark side of the Earth, twice a day they're going to be on the dark side of the Earth, they can actually continue operation. And of course, then the solar panels recharge the batteries. Here's an example of how the satellites are launched, and these are some of the more recent ones at the time of this presentation. There's the Block 2Fs, Block number 9 through number 12, the launch order of them. The last one has just been launched, so the next launch will be the Block 3s. But you see their PRN numbers, this is how we identify them by, and I'll explain what that means a little bit later here, is 26, 8, 10, and 32. The satellite vehicle numbers you can see are 71, 72, 73, and 70. There's the launch states that identify them, the type of clocks they have. So you see 1 cesium and 3 rubidiums. The orbital plane, this is an orbital plane B in position 5. This one here is an orbital plane E in position 6, and this one's an F in position 1. And then the U.S. Space Command number, that's a number that is identified for every object that's launched into space. The codes that these satellites transmit are duplicated every Saturday night at midnight, or better said, every Sunday morning at 0 hours. So they restart these things every Sunday morning. The receivers therefore need the method to duplicate those codes to extract the messages and to actually get the timing. Now what that means is therefore the receivers that we own, what that means is the receivers that we use, in other words your cell phone for instance, has to generate the same codes that the satellites are generating at the exact same time. Now this is done with some initial codes and what's known as a tap feedback shift register. And the tap feedback shift register, what it does is it generates what's known as a pseudorandom noise number. That's your PRN number that identifies the satellite. So each satellite's assigned a code, and then this tap feedback shift register generates a number. And in fact, that number is not random because it's done with a mathematical algorithm, but it sounds random. And in fact, if you listen to this signal, if you tune into it and listen to it, you'd hear basically white noise or static. It'd be like having a radio channel not listening to anything. So let's look at how this basically works. Let's just assume that one of our codes is only 8 bits long, and that's not the case. They're actually longer than that. Sunday at 0 hours, they start off with the initial state. So every Sunday, every week, they start off with this initial state. And what they do is they add the bits. So for instance, they may add bits 2 and 3. In other words, cells 2 and 3 together. So right here we have a 1 and a 1. When we add those bits, 1 and 1 is actually 0 in binary addition. That 0 is put into the lead bit. And then all the other bits, all these other ones are pushed to the right. And the one that's at the end is then broadcast. So what happens is that, and the 1 gets broadcast. If we do that for the next cycle, you'll see we now have a 0 and a 1 here. That 0 and a 1 is now 1, and that gets put into the lead bit. And the other ones are pushed to the right, and the 0 is broadcast. And so that's why they're called a pseudorandom noise number. It sounds like it's noise, it sounds like it's random, but in fact it's not. It's actually a generated code. And that's important because that means our receivers can do the exact same thing. So our receivers are generating this exact same code that the satellite's generating. The only difference is that the satellite, when it's generated, is 20,200 kilometers away from us, so the time of transmission is part of that difference in these two codes. So in other words, they're generated at the exact same time, but they're going to be heard at a different time. And that difference in time is actually the time of transmission. Now, our receivers, again, are passive. But what it requires is we have to have this precise timing mark. So one of these codes is listed as a timing mark. And when that timing mark is matched up, you actually know how long it is. So for instance, let's say this is our receiver code. That was generated, of course, on the Earth. It started at the same time, but now because of transmission time, we haven't heard the satellite yet. What happens is when we hear it, we actually shift that up. There's actually a circuit board that shifts that and matches them up. And the delta time is about 7/100ths of a second. That's all it is from the satellites to us. So that's how code-based receiving works. What it's doing is it's actually generating this code at the same time the satellite generates it. Now, I say the same time, but realize we don't have an atomic clock on our receiver. So there's a little bit of error there, and we'll talk about that later on. But right now, let's just assume they were transmitted at the exact same time. We haven't heard the satellite's signal yet, so once we hear it, we match it up with our code that we generated with our receiver. And then by doing that, we can actually see the precise time that it actually took to transmit that signal, which tells us how far away our satellites are. And if we know the position, that's what the ephemeris data is for. If we know the position of the satellite, we know the control coordinates of our satellite, and therefore we know with the time difference, we know actually our range to the satellite. Now today, most of the satellites are generating 3 different frequencies. Some of the older ones that still haven't been decommissioned are only generating 2. But you can assume that, in fact, by 2020, they all will be generating 3 frequencies or somewhere around that point in time. So we have the L1 frequency, which is at 1575.42 megahertz. So this is what you could tune your radio dial into if you had a radio that could tune into that, and you'd hear that white noise. We'd have the L2, which is 1227.60 megahertz. And we have the L5, which is at 1176.45 megahertz. These L5s are on both the Block 2Fs and the Block 3s. So it's important to understand that the L1 and the L2 are on all the satellites. The L5 are only on the Block 2Fs and the Block 3s. So we have to wait for that constellation to change over. And it's supposed to be done by 2020. That's the end of the modernization period. At least that's what they projected. It's all dependent on funding, of course, so that may shift. Now, the signals themselves, what's important here is they're all based on the frequency of the atomic clocks. The atomic clock has a frequency of this. The L1 carrier wave, therefore, is 154 times that. So that's where that frequency for the L1 comes from. From physics, therefore, that means that the wavelength is about 19 centimeters. Not exactly, but close to 19 centimeters. So if you think about it, 19 centimeters, or just about 2 decimeters, is the length of the wavelength. And that's what we use for our measuring devices, that length of that wavelength. So in other words, if you think about it as from the point of view of an EDM, it's doing the same procedures, except that the receiver has to generate the signal rather than having a splitter that takes the original signal and splits it so that one goes out to the reflector and comes back. We don't have that capability of sending to the satellite and getting the signal back. What we do is we actually just generate our own signal at the receiver. Now, the L1 has both the course acquisition code, that's the civilian code, and the military codes. And the course acquisition code is exactly what it sounds like. It is meant for course positioning and for acquisition of the signal. So we know that this is PRN whatever, number 26. The L2 frequency is 120 times the fundamental frequency of the atomic clock. And this is important that they're all based on this fundamental frequency of the atomic clock. In fact, that's how the system works. That's the important key point of this whole system. That means, therefore, the wavelength is about 24 centimeters. Since the Block 2RMs, the modernized Block 2Rs, we've had the civilian and the military codes on the satellites. The ones before that, and I'm not sure there's any before that right now left. There might be a Block 2A, but they probably won't be by the time you hear this. The fact of the matter is the Block 2RMs may not exist after that. But in any event, these satellites actually are transmitting both military, and the military are the P codes, and now the modernized system is also generating the M codes. The P codes will disappear after they get the system modernized, and the civilian codes, the C codes. The L5 was created strictly for civilian access, and it also has the C code. The frequency of the L5 is 115 times the fundamental frequency of the atomic clocks. L5 has a C code, but it doesn't have the military codes. The important part about the L5 is it has both a code where the C codes are and also a codeless portion, and that makes this a very important signal to we civilians. It has the same chipping rate as the P code, the C code does, and therefore we'll get the same accuracy that the military has today. The L5 frequency has 2 components. It has one with codes and one without. It's important that we have the one without because it'll actually be easier to acquire in low signal to noise ratio conditions. It'll actually improve multipathing protection. It's there for the safety of life issues. The CA code is actually known as the standard positioning service. And this is what we currently have. Its wavelength is about, the C code, in other words, just the C code, not the frequency, is about 300 meters. So it's a 1.023 megahertz chip rate, which means it repeats every 1 millisecond. So every millisecond, every thousandth of a second, this code is repeated, this CA code. That's why it's called a coarse and an acquisition code. It repeats so fast that it's easier for the receivers to acquire that signal. It has an accuracy of approximately 1% of the wavelength, so therefore its accuracy is about 3 meters, and that's all it is. That's not very good for positioning. It's used by the civilian sector for code positioning and timing. And it's also used to lock onto the military and the civilian codes, the C codes. The C codes will have two different civilian codes. There's a civilian moderate, which is a moderate length code, and it has 10,230 bits, and it repeats every 20 milliseconds. There's also the civilian long code. The long code has 767,250 chips, which means ones and zeros, and it repeats every 1.5 seconds. So you can see that we're going from a very long code, 300 meters, to something that's going to be very short. There's no message on the CL code, and that's important because that improves the strength. We don't have to remove the message that's being transmitted on the CL code. It also is going to have the new civilian navigation message. And you got to realize that these codes, as well as the navigation messages and other things on the satellites, are 1960s and 70s technology. And we've improved so much in those technologies that now we can actually bring these up to better technologies, and we'll actually improve our positioning because of that improvement. Both the L2 and the L5 will carry the C codes. On the CL, the lack of data improves the signal strength by 3 decibels, which is about 2 times the signal strength of the present signals. However, because we don't have any data on it, that CL code is going to appear to us to be 251 times stronger than the present CA code. What that means is we're going to get this code in canopy conditions. And again, this was done for safety of life issues. So in other words, if there's a ship at sea that needs to be rescued, or if you're out hiking in the woods and all of a sudden something happens, you break your ankle, you pull up your cell phone, you'll be able to get a signal, and that signal will be able to be received even though you're in a canopy condition. Today, that's not always the case. We'll still need that CA code because we still need it to actually use that C code. On the L1, we're still going to have that CA code because we're going to need it to use the C code, just like the military today uses the CA code to lock into their P code, their military code. The control segment has one master control station near Colorado Springs. It actually is at the 50th Space Wing of the Air Force. It uses the tracking data to predict the near future orbit, or the broadcast ephemeris as known, and the block corrections. In other words, the corrections that it has to do for these satellites. Every once in a while, it'll have to actually move a satellite back into orbit. They get pushed out of orbit because of solar activity, and we'll talk about that later in the AIRS part of it. The mission of this control segment is to collect the tracking data from the monitor stations, compute the orbit and clock parameters, and then upload those and maintain those satellites. In other words, keep them in orbit. There are 6 tracking stations currently used by the Air Force. And I think I showed you this before. Right here they are, the ones with the black stars. Now the National Geospatial Intelligence Agency actually uses these other ones, so there could be up to 19 at any time being used. In fact, 17 look like they're being used and 2 are test sites. Because of the lack of tracking stations, the civilian sector has a capability of having many more tracking stations because it can pool its resources around the world to get better tracking data. In fact, that happened. We created the International GNSS service. It has 200 agencies that pool their resources to provide the ultra-rapid ephemeris, the rapid ephemeris, and the precise ephemeris. And these ephemeres are actually computed at the Jet Propulsion Lab in the U.S. So when you look at this, you see this little cluster of dots around here. Well, that's where the Jet Propulsion Lab is. But you see how many tracking stations the civilian sector has all around the world. So we actually get a much better ephemeris than what the military does provide. Now the user segment, which is us, is primarily divided into 2 segments. There is the military and the civilian sector. We're obviously in the civilian sector. And that's 2 different types of receivers. There's a military receiver that allows those receivers to use the military codes, and then there's a civilian receiver that's restricted to only the civilian codes. The civilian sector can be broken down into different groups also. There's the code-based users, for instance, like us that have cell phones. All of us that have cell phones have GPS in them. Our cars have GPS in them. Those are all code-based positioning systems. It's the largest group of the users. The accuracy is anywhere from 1 meter to 20 meters. And we can get that meter only by processing, either by differential GPS or by wide area augmented system, and I'll talk about this later on in another lesson. The carrier phase shift segment, which is the one we use in surveying, is actually using the frequencies and actually looking at the wavelengths and looking at how much phase shift there is between when the signal was generated and when it was received. It's basically the same method that's used in an EDM. The accuracies are anywhere from 3 millimeters to 2 centimeters. And it's divided into real-time users. The real-time users are people that need their positions right now. That could be a real-time network or a real-time kinematic survey. And then there's the post-process people, but this is where you get your best positions when you post-process this information, and that even goes with the real-time data, and we'll talk about later in other chapters. The civilian users, when they're code-based users, are using that standard positioning service or the CA code. And we use the carrier phase shift measurements. We're the largest segment are the code-based ones, which is about 20 meters approximately currently today at 95%. However, with the modernized system, they expect to get around a decimeter accuracy or about a foot accuracy from the code-based systems because of the L5 and the L2Cs. So you're going to see a real improvement in positioning in the code-based sector. As surveyors, we use the carrier phase shift observations, and we're good to about a centimeter to 6 meters, depending on how we process the data. And that's what you have to realize. We have to process the data in order to get the real accuracies. And that processing can happen real time out in the field, so it's not something we have to do separately. The military and authorized users use the precise positioning service or the P codes or the military codes. So that right now it's the P code. By 2020, when the modernized system is up, they're going to turn those off and there'll be the M1 and the M2 codes. There are different types of receivers also. There's a single frequency receiver that only receives the L1. Then there's multi-frequency receivers, and these receive the L1, the L2, and some of them receive also the L5. Depends on the receivers you have and their age. The more recent receivers will actually get all three of these frequencies. Recognize there's a cost when you do that. Every receiver requires one channel per frequency per satellite. So therefore, when you look at this entire system of satellites, all the satellite positioning systems are concluded, and these are the 4. You have 31 satellites currently in GPS, 24 in GLONASS, 30 in Galileo is predicted, and 30 in Beidou. There are also going to be 5 geostationary satellites in Beidou. So you've got these 4 different satellites. There's going to be a ton of channels that are going to be needed, and of course that's going to up the cost of the receivers. So in this lesson, we simply looked at an overview of the global positioning system. We looked at the GPS signals that it's transmitting, its codes. And in the next lesson, we'll look at the reference coordinate systems that it's working in. And then after that, we'll look at its fundamentals and positioning errors.